Hello and welcome to Landscape Irrigation Week 1. Today we're going to be working out of the Rainbird Landscape Irrigation Design Manual, and we'll be discussing understanding basic hydraulics. In this chapter, we'll be learning about hydrostatic pressure or water standing still, dynamic pressure or operating pressure, which is water in motion, pounds per square inch or PSI, and PSI loss and gains from elevation changes, and PSI losses from friction. Rainbird Landscape Design Manual Chapter 1, Understanding Basic Hydraulics. If you have your Landscape Irrigation Design Manual handy, you'll want to open it to Rainbird, page 3 is what's printed on the bottom of the page. So the first thing you might notice on this page is this really intimidating equation right here. We're going to be breaking this down on the next page. In the Rainbird textbook, on page 3, there's an intimidating looking equation that looks something like this one here. In reality, all you really need to know out of that equation is the bottom line, which is 0.433 pounds per foot in elevation, and that's how much pressure you gain going downhill and how much pressure it takes to go uphill 1 foot of water. And where that's derived from is here you have a cubic foot of water right here, which weighs 62.4 pounds. And in that cubic foot of water, it's 12 inches by 12 inches by 12 inches. There's 1,728 cubic inches in that cubic foot of water. If you take 12 cubes, 1-inch squares, and stack them on top of each other, 12 inches tall, the weight at the bottom will be 0.433 pounds. So that's how that is decided, and so keep that in mind. That's the number you need to remember forever and ever throughout this entire semester. Whenever you're calculating pressure losses or gains due to elevation, you'll always be coming back to that 0.433 psi per foot. This is an image from page 4 out of the Landscape Irrigation Design Manual, and this is calculating feet of head, which is also another way to determine either how much PSI you're going to need or how much PSI you're going to have, depending on how you use this calculation. So in this example, we show here this tank that is 200 feet tall, the column of water from the top of the water to the bottom of the pipe. And so knowing this information, we know that water being able to find its own level will also only be able to go back up 200 feet if it comes down 200 feet. So if somebody decided that they needed to get water 300 feet above a water source and they only had 200 feet of head, they wouldn't be able to do that. And in this equation, you can see that 200 feet comes up to 86.6 psi. And how that's determined is using that number I told you to remember, 0.433 times 200 feet gets you 86.6 psi. Another way to look at that is if you knew how much pressure you have, the 86.6, you could multiply it times 2.31, and that would tell you how many feet in elevation you would be able to pump that water uphill with that much PSI. So keep in mind, if you know that you need to pump water up 300 feet, then you can go ahead and use this equation, 0.433 times 300 feet, you're going to need 129.9 psi to just barely get to the top. So keep that in mind. So where the 2.31 feet comes in handy is understanding its relationship with 0.433. So if you multiply 0.433 times 2.31, you're going to get 1 psi. So basically, it takes 2.31 feet of elevation to create 1 psi of either loss or gain, depending on whether you're going uphill or downhill. This is from page 4 in the Landscape Irrigation Design Manual, and we'll be breaking this down on the next page. So this is from page 4 out of the Rainbird Landscape Irrigation Design Manual, and it's kind of an illustration to show you things that you need to pay attention to when you're trying to calculate how much PSI you're going to have to work with. So here we can see at the street, point A, we have 111 PSI, and that's quite an ample amount of pressure to work with. Normally on a household irrigation system, that's actually quite high. But we do need to calculate other things to go along with that. Some of those things would be friction loss in this pipe between A and B of 6 feet, the friction loss in the pipe in that 3 feet, again in this 3 feet, and then also in this 35 feet. Other things we have to keep in mind is the elevation change of this 3 feet and the elevation change of this 2 feet. Additional items we'd have to pay attention to, which would come in handy in charts in the back of the book, is component losses traveling through a gate valve and also traveling through a meter. So these are things that we'll be discussing later. So now we're going to talk about changes in elevation a little bit more and things to consider. Also remember, if you go downhill, that you have to calculate your gains to your PSI by going downhill. So here in our example on the last page, we had 111 PSI at the beginning, and now we're going downhill 10 feet. So we have to add that in. So we have 10 feet times 0.433 gives us 4.33. Add it to our original 111 PSI that we have, and that gives us 115 PSI at this hose bib. Now remember that this is static pressure. Static pressure means that there's no water moving through the pipe at this time. So had we put a pressure gauge right here on this hose bib, we would see that we have that 115 PSI. But once we open that hose bib and water starts traveling through the system, that's when friction loss happens. And that's water traveling through the pipe and going through components will create losses. In the next couple of slides, we're going to be talking about velocity and PSI losses. Velocity is the rate at which water moves within the components of the system. So what that means is more water traveling through any given size pipe equals a higher velocity. That means the water is moving faster in feet per second. A higher velocity means more friction loss through pipes and fittings. So the more water you put through a pipe, the faster it will attempt to travel, and then it will burn up pressure faster. So here again is that calculation of calculating velocity, but you don't need to do that generally because it's easy enough to open up a chart and figure that out. But if you want to, you can. And you can see down here in these pipe charts, pipe velocity and friction loss charts, that they have a column for velocity and they have a column for PSI loss. So each different size will have its own column for velocity. Pipe sizes, classes, and smoothness along with the speed or velocity of the water all have an impact on the friction losses in your system. We're going to check out a couple of pipe friction loss charts. So here we have friction loss charts for Schedule 40 PVC and Class 200. And what we're going to look at is a couple of different things. We're going to be looking at the outside diameters of pipe, the inside diameters of the pipe, and the wall thickness. And what you're going to notice here is they both have the same outside diameters of 1.05. but their IDs are different. So we have the Schedule 40 is 0.824 on the inside, and Class 200 is 0.93. The significance of that means that the inside is bigger on the Class 200, which means it should have better flow characteristics. Check out the wall thickness. On Schedule 40, it's 0.113 inches. The wall thickness on Class 200 is 0.06, so it's quite a bit thinner. So generally these days, it's not popular to use Class 200 pipe in landscaping, and in some cities it's not even legal anymore. So in general, it's better for landscape irrigation to stick with Schedule 40 PVC if you can until you get into the larger diameters, and we'll talk about that later. So here we have the important things on these charts is the velocity and the pressure loss. So sometimes these charts can be really intimidating to look at because there's so many numbers on there, but what you really need to do is just narrow down what exactly are you trying to do. What you're going to see here on these charts are these gray step down areas, and where those happen are different on each one of these charts. However, they have something in common, and that is at what point they happen. You'll see that they happen when the velocity changes to 5 feet per second. And that's these columns here, velocity, velocity. And the same thing over here, 5 feet per second, or as close as it can get to it, okay? So the industry standard is to not exceed 5 feet per second. And there's reasons for that. If water's traveling really fast and for some reason a valve gets shut or slammed shut, it's like slamming the door in the face of this water, which can cause water hammer. But the other thing it does is it creates a lot of loss by trying to shove more water through a pipe than really belongs through that pipe. So let's take an example. Let's say that we are trying to run a system that's 10 gallons per minute. So what we do is we find our flow rate right here in this column. We come down until we find 10, and we scoot over and we see what size pipe is it once it has left the gray area. Okay, here it is. So what size pipe is that? It's 1-inch pipe. Okay, let's check it out over here in this other chart and see what that is. So here we have our 10 gallons a minute. We scoot over. Well, it happens right away. Well, what size pipe is that? It's 3/4 inch. So you can see that there's some value to that, is that you have better flow characteristics through Class 200 than you do in Schedule 40, but you also can pay the price for that with quality. So in agricultural purposes, a lot of times it makes financial sense to use a thinner wall pipe that has better flow characteristics and be able to get away with smaller fittings than in landscape. But in landscape, we don't want to mess around. We want to go ahead and use the higher quality. Usually our runs are shorter and we don't have to worry about that. So in this particular case, the smallest size pipe we would want to use would be 1 inch. Okay, so the other thing to pay attention to on this chart is your PSI loss. So let's stick with that 10 gallons per minute. Now let's take a look at what our PSI loss is. And that's going to be this column right here. And in this particular case, again, we would follow along our 10 gallons a minute like we did before, and we would end up right here, which is 2.4 PSI loss. Now the important thing to remember here is that that is per 100 feet, because it's just easier for this chart to be made out for 100 feet, because if they did it by the foot, just think about where the decimal points would be, and it would be extended out quite far. So if you traveled 100 feet, your friction loss would be 2.4 PSI loss if you were running 10 gallons a minute. Now if you only went 50 feet, then your losses would be half of that. So your losses would only be 1.2. Just for fun, let's check out and see what the Class 200 is. So Class 200, if you used 1-inch pipe, your losses would be 1.3 PSI per 100 feet. So you can see again the flow characteristics are quite different between the different classes and schedules of pipe. Okay, so if you have your textbook handy, this is when you'll want to open up page 9. And that is, remember, always the number that's in the bottom corner of the textbook page, because if you're in a PDF, the page numbers are not going to match. So that whenever I say a page number, that's what I'm talking about. Okay, so we're going to go ahead and go through this exercise together on page 9 and go through the motions here. Okay, so here we have this exercise where they have a tank that's partially filled with water, And here we show that it is filled 160 feet in this column right here with water. So that's going to be important when we're talking about elevation, because the elevation of the water begins at 160 feet. But when we start calculating friction loss in pipe, then we're going to be looking at this 100 feet instead, because that's the actual pipe underneath that tank. Okay, so keep that in mind. So as we go along, they give you all of these different numbers. So just remember that each one of these numbers on this page is important for a different reason. So here we have 160 feet. That's going to be important for our elevation. Okay, then we have this 50 feet. That's also important for elevation. Then we have the 75 feet. That's also important for elevation, because all of those are going downhill. Then we have a different set of numbers that are important for a different reason. Here we have 80 feet, and that's a distance of pipe in which this water is going to be traveling. We also have this 100 feet, which is going to be pipe. We also have this 100 feet. And the important thing to remember is when we're talking about elevation gains and losses, we're only going to be counting the height. Okay, but when we're counting friction loss for pipe, we always count the distance. Okay, so on this next page, we're going to put this all together. Okay. Question A. So point B in the system is 160 feet below the water surface at point A. Here we go. To find the static water pressure in pounds per square inch, or PSI, at point B, you would multiply what times what and get an answer of how many PSI. Okay, so let's think about that for a second. So we are going how many feet? We're going 160 feet. And remember, the magic number I told you to always remember is 0.433. So that's for every foot of elevation. So we would need to multiply 0.433 times 160, and that would give us 69.28 PSI right here at point B. Okay? So question B. Points B and C are in the same elevation. How many pounds per square inch, or PSI difference, is there in static pressure at these 2 points? Now remember, we're talking about static pressure. That means the water's not moving. So the answer is no difference at all. There's no difference because they're both at the same plane in elevation. So question C, what is the static pressure at the following points? So point D is right here. So what we need to calculate for point D, I make it look a little intimidating, but it really isn't. I'm trying to spell this out step by step. So here we have this 50 foot in elevation gain to point D. So you're going to take 50 and multiply it times 0.433, and that's going to give you your PSI gain for just going downhill, which is this 21.65. Okay. So now remember, at point B, we already had the 69.28. So now we're going to add those two together and come up with 90.93 PSI at point D. Okay, so now point E. So point E, remember, we're only going to count the elevation, not the distance yet, okay? So that's 75 feet times 0.433. gives us 32.475 PSI. And now we're going to add that to the PSI that we had at point D, which was 90.93. And we come up with a total of 123.405. And that is right here at point E. All right. So there you have it. So that gives you your static pressure. So here you can see at point E, it looks like there's a little valve right here that's just shut off. So if you just had a pressure gauge down there and no water's moving whatsoever, it's going to show you about 123 pounds. So now what happens when you open up that valve? Well, water starts traveling, velocity picks up, and then you start getting into friction losses. So now we're going to take that into consideration and come up with what the dynamic pressure is going to be at different points within the system. Okay, so something you're going to need to know is what is the flow rate. For you to be able to read a pipe chart, you're going to have to know what the flow rate is. You're also going to have to know what size pipe you have. So they went ahead and told us that this is going to be 1.25" class 200 pipe, and that it's going to be a flow of 26 gallons per minute. So we're going to take that into consideration and look at this chart. I kind of shrunk the chart down so we're only looking at what we really need to look at here. And that is, follow this arrow right here down to 26 gallons per minute, right? And here is our PSI loss for 100 feet. Remember, the chart's always 100 feet. Okay, so point B had a static PSI of 69.28. Okay, so now after you subtract the friction loss caused by the 26 gallons per minute through 100 feet of class 200 pipe. Now remember, this is the pipe that we're calculating for friction loss, so it's the 100 feet. Ignore the 160 feet now. So 100 feet, we already see, since the chart is 100 feet, is it's 2.46 pounds. So we're going to take the 69.28, subtract 2.46 pounds, and end up with 66.82 pounds left over. So now that's how much we have to work with at point B. Okay, so now keep in mind that dynamic pressure is a running total of friction losses and elevation losses or gains. So you've got to keep in mind that you might want to be doing different activities at different points. So at point B, you're going to have 66.82 psi. But if that wasn't enough to operate, some type of elaborate sprinkler that requires a higher psi, you wouldn't be able to use it there, but you might be able to use it down on point E, where the psi is going to be much higher. So knowing how much you have at each point can be useful. Okay, so starting with point B's dynamic pressure, answer the following questions. So what is the dynamic pressure at point C? Okay, so if we take what we had left over from point B, which was 66.82, then we need to calculate what the friction loss is in that 80 feet of pipe. Okay, remember, it's 80 feet. Well, this chart of the 2.46, that's for 100 feet. So how are you going to figure out how much you lose in 80 feet? Well, this is the easiest way for me to tell you. Remember that it's 80% of 100 is 80 feet, okay? So that's why we're going to take this and go times, we're going to take 0.8, multiply it times 2.46. That's going to get us what our friction loss is in that little hunk of 80 feet of pipe. So we're going to take 66.82 and we're going to subtract out what 0.8 times 2.46 is, and we're going to end up with 64.85. So you can see these are not significant losses, but if you're going a long way, sometimes it really can add up. Okay, so same type of principle for point D. Okay, so remember though, what happens different from point D is that not only are we traveling 50 feet and we're going to have some friction losses in there, but we're also going downhill 50 feet. So we're going to gain some of that back, right? So you'll see this equation is going to be a little bit longer. Okay, so we're going to start out with our 64.85, and then we are going 50% of 100 feet. We're only going 50 feet. So it's going to be 0.5 times 2.46. Okay, then also we're going 50 feet downhill, so we need to add some pressure back in from the gains we just made, which is 50 times 0.433, and now we're going to have a dynamic pressure of 85.27 at point D. Okay, now for the grand finale, point E's dynamic pressure is going to take what we had ended up at point D, and that's 85.27. And now we have those same two scenarios again. We have some losses in there, and we also have some gains. So being that this distance is 100 feet, we're going to take that 85.27 and subtract 2.46 because it is 100 feet off the chart and it is 100 feet here. Then we're going to add in what our gains are. So that would be our 75 feet in elevation times 0.433, and you add those all together. So you take 85.27, you subtract 2.46, and then you add in the gains of 75 feet, and your grand total is 115.28 psi. So I went through that pretty quickly, and you might be shaking your head just going, what the heck just happened? That's a lot of stuff to take in. Okay, so the point in this textbook is to take you through every little step so that you know how to do every single little step. There are easier ways to do it, but it comes down to needing to know how to do this if you needed to backtrack and take a step in a different direction. So I'm going to tell you a little bit of a shortcut now that we could have done. What we could have done is added up all of our elevations at once. We could have said, okay, you know, we have 160 feet plus 50 feet plus 75 feet, added those all together, multiplied it times 0.433 to get all of our gains, right? Set that aside. We could have then also taken all of our pipe distances, 100 plus 80 plus 50 plus 100, figured out all of our losses, added them all up together, and would have been a little bit easier to do all of that. So as we move forward when we're doing projects together, I'm going to try to do it the easier way, but in this particular exercise, it's important for you to see step by step. And actually, I'm going to backtrack on that a little bit. So throughout this chapter, there will be a lot of little baby steps on figuring out what friction losses are going to be in the next upcoming chapters. Okay, so just so you know that the answers are in the back of the book for all of the exercises that are at the ends of the chapters. And those will not be assigned to you, but those are a great way for you to check and make sure that you're understanding the process. I will tell you there's a couple of wrong answers in the back there. They have a decimal point in the wrong spot, but in this particular chapter, all of the answers in the back are correct. So when you go to that solutions page, there's actually several pages. You'll have to remember what chapter you're in to be able to find the answers. Okay, so here's an example of the solutions page, which it looks like it's page 89 in the Rainbird textbook. And here I have circled what the equations were that were relevant to this particular chapter. And the next chapter also has the answers, you know, followed up right in here. So keep that in mind, that this is a good place to practice. So good job, you survived the first chapter lecture, and I hope that this will be easier for you to go online and do the exercise. I think I took it easy on you guys this week, and look forward to seeing you at the lab.